All right, Gen Chem kids, we are going to talk about polarity of molecules today. So now that you know how to do Lewis structures and you know how to determine the shapes of those Lewis structures, now we're going to put the electronegativity of the bonds on those shapes and determine whether that molecule is polar or not polar. Now, polarity is basically, do I have a side of a molecule that is a little bit more positive and another side that's a little bit more negative than it normally would be if we shared electrons evenly? So we say that it has poles. It will have a negative pole and a positive pole just due to the electrons that are being pulled one way or the other due to the differences in electronegativities of the various atoms that make up that molecule. So when electrons, let's get into this, when electrons are shared unequally, a dipole is created. And we talked about dipoles a little bit before. We talked about how if I had a bond between carbon and nitrogen, and if I look at my electronegativity chart here, let's highlight carbon and nitrogen. Carbon has an electronegativity of 2.5 and nitrogen has an electronegativity of 3. 3 is bigger than 2.5. So that means that nitrogen would have more of its share of the electrons that they are sharing in this bond right here than carbon would. So that would mean that when we actually drew this molecule, not draw it, or when we actually look at how this molecule behaves in real life, because nitrogen has more of its share of electrons, it's going to have a partial negative charge over here. And carbon would have a partial positive charge, hence the term polarity. I have a positive pole on this side of the molecule and a negative pole on that side of the molecule. So now we're going to start looking at that on molecular shapes. Okay? So I like to think of dipoles like tiny spaceships that are pushing or pulling atoms in that molecule away from each other or towards each other. And we're going to look at this in relationship to the central atom. So we're going to add up all those dipoles or all those little spaceships that are pushing and pulling on the center atom. And if that center atom moves, that molecule is considered polar. That means it has a positive end and a negative charged end. Okay? If all of those little pushes and pulls add up and cancel out, if that molecule or that center atom stays still, that molecule is considered nonpolar. Okay? So we're going to start looking at these geometries really quick. So that's my analogy is little spaceships pushing and pulling. That's why we've got pictures of the Starship Enterprise. Now my question is, are all spaceships the same? By relationship, are all dipoles the same? Are they all the same? Do I have differences of electronegativities that are the same all the time? No. Sometimes the difference of electronegativity is really large. And if that difference is really large, then I have a very polar molecule. Sometimes the electronegativity difference between the atoms that are in that bond is very, very small. And if it's so small, then it's not even really polar. This would be a nonpolar molecule, even if I do have a difference. If that difference is very slight, then it's going to be nonpolar. So basically, we've got a scale here. So if I have, and we are going to use the same scale, if I have a difference of electronegativity that is less than Let's write that again. If I have a difference of electronegativity that is less than 0.4, so there's not that much of a difference between atoms, this is going to be nonpolar. And we also have to look at, do the dipoles cancel over the geometry of the molecule? Then our next step is if our electronegativity difference is greater than 0.4 but less than 1.7 and doesn't, let's spell that correctly, doesn't cancel out. Now, by canceling out, we're going to look at how these dipoles add up in a minute. If I have an electronegativity between 0.4 and 1.7 and all the dipoles don't cancel out, that molecule will be polar. Okay? So there's our scale of electronegativity. So we're going to consider the following, and these are all Lewis structures that we've drawn before. Okay? So I'm going to just draw them really quickly, and then we're going to look at the three-dimensional shape. Okay? So pH3. We've got this shape right here. So this will give me a trigonal pyramidal. Shape for my molecular geometry. The next thing I need to do is look at the difference in electronegatividity. So I'm going to look up the electronegativities of hydrogen and phosphorus. So phosphorus is 2.1 and hydrogen is 2.1. Okay? Excuse me. So if I subtract the two, the difference here is 0. Now, a lot of people would say, oh, the difference is 0, so there's no electronegativity. This is where there's no polarity. This is where the geometry has to be looked at, okay? So I'm going to show you a FET that's going to be really, really important for you to look at. Let's see if I can get the keyboard up here. So if we type in FET Colorado, so we're going to go to fetcolorado.edu, and we'll probably use this for a lab next time. We're going to go to chemistry, and we're going to look at molecule shapes right here. So we're going to do this. We're going to do molecule. Now, if you've realized on this example that I drew, we have 3 bonding areas and we have 1 lone pair. So I want to put that into this FET. So right now I have 2 bonding areas, so I want to put in another one. And I also want to put in a lone pair. Okay? So now I can show my bond angles, I can show the electron geometry and the molecule geometry so that you guys can get your shapes here. Now, look at this. I've got this whole area on the far end of this molecule that's just electrons. It's just negative. With these hydrogens down here that are going to be just 1 electron each. So this end of this molecule is going to be pretty negative just because it has electrons. So even though the electronegativity is not very different in terms of having a difference between the values of the elements, just because we have that area of electrons that is very much alone and it's just electrons, this is going to be polar just because of that lone pair up at the top right here. That's going to make it polar. Okay? Carbon tetrachloride. So here we go. We have a Lewis structure like this, where we have chlorines all the way around, all four. So we have 4 bonding areas, and they're all bonding, so we have a tetrahedral shape. The next thing we want to check is our electronegativity. So carbon is 2.5, chlorine is 3. So the difference between 2.5 and 3 is 0.5. So that does give us a fair amount of electronegativity difference. So let's see, carbon was 2.5, chlorine was 3. So our difference is 0.5, so that very well could be polar. Now let's look at our 3-dimensional shape. So if I look at 4 bonding areas around that center atom, let's look at that. So I'm going to take off this lone pair, and instead of having that lone pair, I'm going to add another single bond. Now, notice I have a tetrahedral shape, and I have a tetrahedral electron geometry. All my bond angles are 109.5. Every single one of these is the exact same distance away from each other, and because they're all chlorines, they're going to be the exact same pole. So if I have the exact same pole going opposite ways, what happens? If I have 2 strong friends pulling at me the same strength on opposite ends, can I move? No, I can't. I'm kind of stuck in the middle. I'm being pulled, but I'm stuck. Those dipoles or those forces, because they're all equal and going all opposite each other, will cancel out. So because these dipoles cancel out, the dipoles cancel. So because of that, this becomes nonpolar. Okay? Hydrogen fluoride. We have HF, and let's look at our electronegativity. So hydrogen, we looked up before, it's 2.1. Fluorine, let's look at fluorine. Fluorine is 4.0. It's the highest there is on the table. So hydrogen, 2.1, fluorine is 4.0. That gives us a difference of 1.9. That's really, really, really strong. So that hydrogen does not have its fair share of electrons. Most of the electrons are going to be pulled toward that fluorine end. So this is very polar. I'm going to have a very negative end here on the fluorine and a very positive end here on the hydrogen. So this is indeed polar. Okay? All right, hydrogen sulfide. We have sulfur in the middle, and we have hydrogen at the end. So there's the Lewis structure for hydrogen sulfide. Let's look up our electronegativities. So hydrogen is 2.1. We've already done that a few times. Let's look up sulfur. Sulfur, we have 2.5. So sulfur, we have 2.5. So our difference here is 0.4. It's right on that border. So let's see if the geometry makes that so that means that the sulfur is a little bit more electronegative. So that means that the electrons will be pulled towards the sulfur. Okay, let's look at the FET and see if that gives us a shape that we can see if it cancels out. So I don't have 4 bonding areas on this. I have 2 and 2 lone pairs. So I'm going to put 2 more lone pairs. Okay, so remember, sulfur is this center purple atom and hydrogens are these atoms right here. So we said that the electrons would be drawn towards the sulfur, right, from the hydrogens, because sulfur is a little bit more electronegative right here. And then I also have these electrons on the sulfur. So wouldn't it make this whole end of the molecule with sulfur negative? And then this end of the molecule with the hydrogens positive? It would. So this is going to be polar. Okay? So because of that shape, this will end up being polar. Because it's not really a line like this. It's really more of the lone pairs being like this and the hydrogens being like this. So we do end up having a fairly negative area right there and a positive area right here. Okay, so let's do our next one. Okay, our next one, we have silicon tetrafluoride. So silicon and fluorine. Silicon's going to be in the middle, and I'll have 6 or 3 lone pairs on each of the fluorines. Okay. Now, let's look at silicon's electronegativity, and we already looked at fluorine. Fluorine was 4.0, which was really high. Let's look at silicon. Silicon has an electronegativity of 1.8. So, when we look at that, 1.8. So the difference here, and notice I'm always taking the absolute value. There's no negative values in difference here. So this will be 2.2. Yeah, 2.2. That's really, really high. High enough that, because we have a nonmetal bound to a nonmetal, this is still covalent. But in terms of our scale, we would think of this as ionic, right? This is where that scale kind of fails us because it doesn't always catch everything. Okay, let's look at the FET. So if I have 4 bonding areas, so I'm going to take out these lone pairs. So I have 4 bonding areas, and they're all bonding the same element. We've got the silicon here in the middle. We've got the fluorines on the sides, and they're all the same distance apart. So wouldn't they cancel each other out? They're all the same strength, and they're all the same distance apart. So because they're all the same strength and they're all the same distance apart, all those dipoles end up canceling. So on this molecule, even though the individual bonds are very, very polar, the dipoles cancel. So these dipoles cancel, so this ends up being nonpolar. All right? Now let's look at fluorine. So if I draw the Lewis structure for fluorine, I get this. And if I look at the electronegativity of fluorine, I have 4.0 and 4.0. So the difference between 4 and 4 is 0. So because there's no difference, do I have any difference on the pull of the electrons? It's like if I get 2 super heavyweights to play tug of war. they're going to cancel each other out because they're both the same strength. So this is nonpolar. Okay, let's look at nitrogen trifluoride right here. So if I have nitrogen trifluoride, it is slow in changing my ink colors. Okay, this is my Lewis structure here. We're going to look up nitrogen, and we're going to look up fluorine. We've already looked up fluorine. So let's look up nitrogen again. Okay, nitrogen is 3.0. Fluorine is 4.0. So 3.0 and 4.0. So the difference between these two is 1. That's definitely enough to make a polar bond. Now, the fluorines are more electronegative, so the electrons are going to be pulled toward the fluorines. So let's look it up on PhET. We've got 3 bonding areas and 1 lone pair area. So if I take off one of these bonding areas and add a lone pair instead, remember these little gray atoms right here are the fluorines, and this purple atom here in the middle is the nitrogen. So I'm going to have the electrons pulled from the nitrogen towards the fluorine. They're going to be going this way, and this way, and this way. So this is going to be negative, negative, negative. And I also have this where this is negative as well. So if I have negatives all around the outside, do you think that's going to be polar? Not too much. Okay, that's not going to be super polar because I have negatives all the way around the outside. So those dipoles kind of cancel, especially with the lone pair. So not that polar. Not polar. Okay, let's look at carbon hydrogen trichloride. So carbon's going to be in the middle. I'm going to have 3 chlorines, and I'm going to put them all along the bottom. And I'm going to have the 1 hydrogen. Now the thing is, we have a couple of bonds. We have a bond between the carbon and the hydrogen that we need to look at. And we have a bond between the carbon and the chlorine that we need to look at here. So carbon, let's look up carbon. Carbon is 2.5 and chlorine is 3.0. So let's look at that bond first. So carbon is 2.5 and chlorine is 3.0. So the difference there is 0.5. That's definitely enough to make something polar. So that means that when I look at this, chlorine's more electronegative. So I'm going to have electrons pulled this way, and this way on those bonds. Okay, let's look up carbon and hydrogen now. So carbon is still 2.5. Let's look at hydrogen. Hydrogen is 2.1. So we're going to put hydrogen as 2.1 here. So the difference here is 0.4. Now, carbon is more electronegative than hydrogen. So when we look at this dipole, it's actually pulling towards the carbon. Okay? So let's look at this on the PhET. So if I look at this on the PhET, I have 4 bonding areas and no lone pairs. We're going to pretend that these 3 over to the left are all chlorines. So the electrons are going towards the chlorine and towards this chlorine and towards this chlorine. And this one's the hydrogen. Electrons are going down towards the carbon here in the middle. So electrons are going this way, this way, this way, and this way. So that means this end of the molecule is negative, and this end of the molecule is positive. So this will be polar. So this is a polar molecule because the electrons are all pointing towards the chlorines. Okay? A few more examples. Okay, oxygen. We have oxygen double bonded to itself. Now, the electronegativity of oxygen is 3.5. And both of them are 3.5. So the difference is going to be 0. So am I going to have any polarity between two equally strong things? No. So because they're both equally strong and they're both pulling on the electrons the same amount of strength, this is going to be nonpolar for the oxygen. Okay, let's look at carbon dioxide. So carbon dioxide, I will have carbon in the middle, and I will have oxygens double bonded. Okay, so if I look at the electronegativity for carbon, carbon is 2.5 and oxygen is 3.5. So my difference here is 1. Okay, now oxygen is more electronegative, so that means I'm going to have a dipole here and I'm going to have a dipole here, pulling out towards the oxygens. Let's put that in the FET and see if indeed that molecule is linear and see if that does indeed cancel out like it looks like on paper. So we got 2 double bonds. So let's take all these single bonds off. And I've got 2 double bonds. Okay, what does it look like for that molecule? Is it linear? Is that dipole going to cancel each other out because they're oppositely and opposite opposed? Yes, they are. Okay, so they will cancel each other out for sure because I've got one pull in here and I've got one pull in here and they're both the same strength. So that will cancel out. So this is nonpolar because those dipoles cancel out. Okay, let's look at carbon monoxide. We have a triple bond like this. Carbon's electronegativity is 2.5 and oxygen's is 3.5, so we get a difference of 1. Okay, oxygen is more electronegative. So let's look at the FET. Does it indeed pull the way it looks like? So let's take these double bonds off. Let's put on a triple bond. We're going to pretend that the gray is the oxygen and the purple is the carbon. So we said that the electrons were pulled towards the oxygen. That means this oxygen end is going to have more than its fair share of electrons, so it's going to be negative. And the carbon won't have as many electrons as it should have if it was sharing evenly. So this is going to be positive. So indeed, this will be polar. Okay, so this will be polar. Okay, and then last but not least, we have cyanic acid, where this is the Lewis structure. Now, we have to do a couple of bonds here. We have to look at carbon and hydrogen, and we have to look at carbon and nitrogen. So carbon is 2.5, hydrogen is 2.1, so our difference here becomes 0.4. So carbon's more electronegative, so that means we're going to have electrons pushing towards the carbon. And then carbon is 2.5, and we looked up nitrogen before. Nitrogen is 3.0. So our difference here is 0.5. Nitrogen's more electronegative, so we're going to have electrons pushing towards the nitrogen. So let's put this in our FET here. So if I have a triple bond and I have a double bond, and let's put it in the orientation that we drew on our paper. So this is going to be our hydrogen, this is going to be our carbon, and this is going to be our nitrogen. We said electrons would be pulled from the hydrogen towards the carbon, and then pulled from the carbon towards the nitrogen. So that means the electrons are really going to be focused around the nitrogen. So we're going to have a partial negative charge right here. And hydrogen is not going to have its fair share of electrons, so it will have a partial positive. So we're going to have a positive end here and a negative end here. So this will indeed be polar. Okay, so cyanic acid is polar. Okay, so guys, on your homework today, you can use this FET if it helps you construct the molecules that I'm asking you to use. Use the FET and see the three-dimensional shapes, and we'll talk about forces of traction later in IMS. Have a great day. Thanks. Bye.